Hi again, AP Calc gang. Here's lesson 7-2, areas in the plane. And this is a pretty intuitive lesson, I think, as we're going to be employing integrals to figure out various areas, but the regions are a little bit unique, and so that's what makes some of these a little bit tricky anyway. Anyway, here's the main meat and potatoes for this particular lesson anyway. So the idea is that if we have a couple of continuous functions, we'll call them f of x and g of x as they're illustrated here. Notice f of x is greater than or equal to g of x over this whole interval. These are continuous functions. So the area between them, this is what we're looking for in green here, is the integral of f minus g from a to b. Here's what that integral looks like. So f of x minus g of x dx. Kind of makes sense if you think about it. Remember, if we just took the integral of f of x by itself, that would be the area under the curve. That would go all the way down to the x-axis here. That would be this whole big region here that I'm highlighting right now. If we just took the integral of g of x, again, that would be the area under that curve to the x-axis. So it would make sense that if I had this whole big area here, and I subtracted out this area here of g of x, yeah, I'd be left with this green section here. So I think it's pretty common sense or intuitive that this would actually work. Now let's take a look at a few examples. Alright, we'd like to find the area of the region between y equals secant squared x and y equals the sine of x from 0 to pi over 4. So I tried to draw that here a little bit. The sine of x would be this function right here. Let's see if I can find there we go. Would be this function right here, and the secant of x would be this function right here. So I'm trying to find that between 0 and pi over 4, which should really be right about here. Well, first of all, let's see if we can do this just old school method here. So what we're looking for then is this particular area. We said it's going to be the integral. By the way, both of these functions are continuous, at least in this interval anyway. And one is certainly greater than the other throughout this whole interval. So from 0 to pi over 4, and the one that is greater is the secant one. So it's going to be secant squared x minus the sine of x dx, like that. Now, looks a little complicated, but these should be integrals that we can evaluate fairly readily here by using antiderivatives. Can you think of the antiderivative of secant squared? Well, yeah, that's just going to be the tangent of x, because the derivative of tangent is secant squared. And what about sine? Well, we know that the antiderivative of sine is negative cosine. When we have this negative sign already here, this minus sign, so minus a negative, that's going to be plus the cosine of x. No plus c here because we do have an upper and a lower bound to integrate here, so it looks just like this. So what this will end up to be is the tangent of pi over 4 plus the cosine of pi over 4. We'll get an answer for that. And then it'll be minus, let's put that minus here, minus the tangent of 0 plus the cosine of 0, like that. Now if we figure out each of these, the tangent of pi over 4, that's 1. And the cosine of pi over 4, if you remember from your circle chart, that's that square root of 2 over 2. Meanwhile over here, should probably just put an arrow in there like that. The tangent of 0, if we think about that, tangent is sine over cosine. Sine of 0 is 0, but the cosine of 0 is 1, so that's going to be 0 plus the cosine of 0 is 1, as we said. So out of all this, what we're really going to get is 1 plus the square root of 2 over 2 minus the second part here, which would actually be 1. Those 1's cancel out. We get the square root of 2 over 2. Keep in mind, that's this particular region right here. I'll try to color it in. between 0 and pi over 4. I've set up my scale so that's where it is. Now just to check this on our calculators, I entered in those particular functions in y1 and y2, and I just used the numerical integral to calculate it, and sure enough that 0.707 is exactly the same as the square root of 2 over 2, so that works. Alright, here's another different type of problem. Determine the area of the region enclosed by y equals x squared and y equals the square root of x. Well, again, we would like to try to figure out which function is on top or which one is higher. Certainly the graph here shows us that the square root of x is it. So we know then that the integral we want to take is going to be the square root of x minus x squared, like this, dx. Now, what we don't know maybe is the intervals. It certainly looks like 0 should be the lower interval. It looks like 1 might be the upper interval too. Notice if we put 1 in place of x in each case, sure enough it would equal 1. So that's what it is here. Sometimes we might have to use our calculator or a little algebra to figure out where this intersection point, or maybe more than one point, is on these types of integrals. Anyway, let's see if we can finish this up. So this is, remember, the square root of x is x to the 1/2. So if I did some antiderivatives, then I think that's going to end up to be, remember we increase by 1, so 1/2 plus 1 is this, x to the 3/2. Does need to have a 2/3 out in front of that though in order for that to work out well. And then by now, of course, we know the integral of x squared is 1/3 x to the 3rd. And we want to evaluate that from 0 to 1. Well, really the 0, 1, I think we can see will just give us 0. So if I put 1 in place of x, well, 1 to the 3/2 power is just 1. 2/3 times 1 is 2/3. Same thing here, if I put 1 in place of x, I'll just get 1/3. So 2/3 minus 1/3 is actually 1/3. We could verify that on the calculator, but again, that's going to be the area of that particular region. Last one we want to take a look at here now is this particular one. Now notice the difference here is that instead of this function or this relation written in terms of y, it's written in terms of x. So x equals 1/2 y squared minus 3, and x equals y plus 1. Now up to this point we've been trying to say top minus bottom in trying to evaluate these integrals, but when they are written in terms of x like this, then it's often wise to integrate them with respect to y. And so then, instead of taking the top minus the bottom when we do this, it's actually going to be the right function minus the left function is the strategy we're going to use here. And that's probably a decent thing to write down here. I'm going to just write that. So when we have these functions written like this, when it's x equals something, we are going to take the integral of the right function minus the left function, if that works out that way. So I think we can see in this case, and by the way, then when we try to figure out our intersection points, we need to figure out not so much the x coordinate, but now what's the y coordinate going to be here where they intersect. So that's just the opposite of what we did before. So in this particular case then, it does look like it's going to be from -2 to 4. Again, both of the examples we've done here, you can readily see that. Some of them won't be quite so apparent. So in this case, the function furthest to the right each time is the y plus 1, and the other one furthest to the left is the 1/2 y squared minus 3. Again, we would say now dy instead of dx in this case. If we put them, both of these together here now, we will get -1/2 y squared plus y, and then I really have 1 minus -3, I think you can see that, so that's going to be plus 4 dy. Well, again, this should be one that's not too tough to just use antiderivatives on. So here's my y squared. I know that's going to be something to the third power. And when I take the derivative of that, it's got to end up with a negative 1/2. So I think it's going to be this, negative 1/6. If we think about that, 3 times 1/6 is 3/6, which is negative 1/2. Plus 1/2 y squared plus 4y, like that. We evaluate that between negative 2 and positive 4. I'm going to let you verify this. I'm not going to do all the grunt work here. This is going to actually end up to be 18 is our final answer there. Alright, so thanks for watching. That's all we're going to do here. We'll be practicing on these for like 3 days in class, so I think we'll be able to do these pretty well. So thanks for watching. We'll see you guys in class.